Scott. You are the remote audience. It's a big pleasure to be here. This venue is very special. I started to work with surveys when I arrived here as a postdoc of Rogério a few years ago. And today I want to talk a little bit about measuring the universe with the galaxy surveys and what we have been doing and what we are planning to do in the future. So my name is Felipe Andrade-Oliveira. I'm now assistant research and lecturer at University of Zurich. My official position is Albert Assistant. Maybe this is the best translation I could find. And I've been working in several projects. So for the dark energy survey, I've been working with the theory and combined probes, where I'm one of the coordinators. I'm also a builder in the dark energy survey, given what I did for the infrastructure. For the LSST desk, I'm a full member, and I've been working with covariance. I'm a pipeline scientist for 3 years, and I'm also the co-convener of the group of covariance. I will get in details soon. Also for the DESI, the spectroscopic instrument, I've been working there and I'm doing more instrumentation, but I also work with in-kind contribution when I was a postdoc here. And I'm joining now LIGO. I have a student working LIGO and I'm joining so we can, I can give him some support. So I was expecting to have more students here, so I dedicated some slides to show about what we are doing now. In January, we started in UZ8, so Marceli was moving there as a professor, and I'm her Uber assistant. Our group is starting, so we are going to be the group of cosmology there, and we have a postdoc that's starting now, Dani Laghi. Also, in November, we're going to have a new postdoc that's also an awesome guy, but I don't know if I can tell his name for a while. We have our graduate student that's coming from Michigan. So Isaac McMahon, he's working with GW localization and work with some of the pipelines of LIGO. Sean McBride, he's my lab buddy. We spend a lot of time together working with the DES instrumentation. Simran, she's a grad student that's working with LSST. Nora Sharma is a specialist and searching for counterparts in optical. That's a very, very hard task. And Lucas Faga, he visited me. He's my grad student here in Brazil at the University of São Paulo. And he spent 1 year with me there, where we work with covariance and with the harmonic space analysis in the dark energy survey. So if you know grad students that want some opportunities, we have a good opportunity. We are building this new group. Also, the institute, we have this big image in the entry of the institute. And we have 5 Nobel Prize here: Schrödinger, Einstein, Miller, Max von Laue, and Röttinger, the guy of our X-ray. You know this and this. This is from superconductivity, and he's from crystallography. So sometimes the doors close out of the blue in Zurich, and we wonder if Einstein is haunting us. So to start this, I'm gonna start talking about the current model of cosmology, of standard model of cosmology. It was consolidated in the end of the last century with the supernova results from the lambda. So as far as we know right now, the universe is made basically by the dark energy, or the best candidates now is the cosmological constant with 68%. So dark matter that we know for a long time, since Zwick and Rubin, that's made in 26%, and also is fundamental for the galaxy formation. The baryonic matter, that's basically what form us and this institute and everything that we see in the periodic table. That's less than 5%, and also radiation and neutrinos that has a very important role, mainly in the early universe, mainly for the radiation. And this model has been successfully explained a lot of observations, a lot of the observations from different nature. This is the cover of Science magazine when I discovered the accelerating universe. And it's not surprising that it's called the concordance model, because after decades in the last century of a confusion about the curvature or the dark matter content, we finally found something that could explain different observations. But this is not the end of the story, because recently we had some indications of tensions. So experiments mapping the early universe, like the CMB, is giving a different value for the local expansion, the Hubble parameter, then Cepheids, and then the tip of red giant branch. We noted that we have these very distant values and error bars for both cases. We still didn't detect properly the dark matter particle, and it sounds like a very hard task, but until we can detect some candidate, it's hard to guarantee that the dark matter is a particle, or which kind of properties we can have beyond the astrophysics that we are observing now. Finally, we have the lambda, or the dark energy. If you believe in the Zeldov approach for the cutoff and for the fundamental fields, we're going to have a huge mismatch. If you don't believe in this, we still need to explain why it's the same order of the density of energy is the same order of the other components, and it looks like some fine-tuning problem. So in the past, I was doing models of dark energy. Now I'm more working with observations and with cosmological tests. And we have a lot of address. And if in the past I was thinking about creating models that could pass the possibilities, now I'm more interested in reduce the possibilities and getting better constraints for what we have in cosmology. So a successful approach for tackle this question is what we call the cosmic cartography. This is a figure from our colleague in DESI, Claire Lemon. And it's showing the maps that we created in surveys. And here is the galactic plane. And the idea is that we can trace the universe and the perturbation, the invisible part of the universe, by these tiny luminous things that we call galaxies. And for the galaxies, we can use both the positions and the shapes to try to understand what is happening in the invisible structure. Given that, we can compare summary statistics, we can extract some model or something that we can compare with our model, and try to measure the components of the universe. I'm here talking about two flavors of cosmological surveys, galactic surveys, actually. I'm talking about galactic surveys using imaging. That's the case here. So in this case, we have low resolution in the wavelength, so we don't have a lot of information about the spectra. We need to use templates in order to find what's the redshift, how far are the objects from us. And, but on the other hand, it's way cheaper, and we can map very, very large portions of the sky. And we can use very creative strategies like dividing everything and combining tomographic beams and try to analyze this concentrated information in these shells of the universe. On the other hand, we have the galaxy survey with spectroscopy. This has a very nice resolution, so we can measure properly the distance, the redshift, actually, of the galaxies and the other objects. And, but this is more expensive, this is harder to do, and just recently we could do this in a unprecedented scale that I will detail in the next slides. So here's a schematic picture of how a galaxy survey works. In the case is for the LSST. So we have a telescope that has a big field of view and a camera with a great resolution like the DE-CAM or like the new cam that we are constructing that we are now installing in the LSST. And with this camera, with this very, very nice resolution, we can point in regions in the space with some strategy, and we can collect samples and the collected information of the galaxies, and also shapes, photometric redshift, and we can combine this in tomographically. The current generation of the photometric surveys, we have the Hyper Supreme camera in Subaru, the KIDS, the kilodegree survey, and the DS that has the largest footprint. The Hyper Supreme camera is a very nice experiment. They have a huge density of galaxies, but they have just small regions. And the DS has a very nice curvature of the sky, but not with the same density as the Hyper Supreme camera. So talking about the DS started a long time ago, before I arrived here in IFT. And DS is a big imaging survey with more than 400 members, involving institutions from the different countries, 7 different countries, 25 institutions. In the core of the DS, we have the D-CAM. The D-CAM was the best camera by its time. It has 507 megapixels. And it has also 5 filter bands. It has a very nice degree of field. It was installed in the Blanco telescope. And it collected data for 5.5 years and almost 5,000 square degrees. So this is a little bit more than 10% of the sky. We collected now 300 million objects. This is a very nice number. And for the public generation of the DS, that's the year 3, where we had 30 papers. The DS final analysis is coming soon. We are being a coordinator of the TCP. We are trying to push, and it's a lot of work, but we are trying to finish this summer. So in the DS, I work with theory combined probes, and I also work with harmonic space, covariance. I did some pipelines for the BAO, and also anything else that my dear colleagues needs from me. So give this nice setup. We have 3 big questions to try to address here. So the first one is if the late universe, the universe that we see now with the dark energy, is consistent with the early universe. And by consistent, I mean if the universe is explained by the same model. The second one is the growth of structure and the expansion measurements agree to each other. And finally, maybe this is the holy grail, if the dark energy density can change during the evolution of the universe. So if you have something that's different from the lambda CDM, or from the lambda, actually. So the cosmology and the astrophysics in the dark energy survey is very rich. We have several probes talking just about cosmology and forget about all the nice work that people are also doing in solar system, trans-Neptunian objects. We have some main subjects like supernova and BAO, gravitational waves and strong lensing, measuring the history of the expansion. And measuring the history of growth and the history of expansion together, we have our measurements of large-scale structures, weak gravitational lenses, and galaxy cluster counts. So today I'm gonna focus more in these three cases here, but since I have this amazing audience here, I want also to talk very quickly about gravitational waves, and I'll talk a little bit about supernova and our latest results. Okay. So this is a very pictorial way of thinking what we do. This is the main probe of the DS. So the DS collects shapes of the galaxies and collects the position of galaxies. And we have two different samples, two different categories of samples, actually. We have what we call the source galaxies that are very backgroundish galaxies. And we have these foreground galaxies that we call lenses. So the source galaxies, here we have a very circular galaxy. And when the light crosses the space-time with all the distortion from the gravity and the distortion from what I try to depict as an invisible halo, it got to our telescope very distorted. Not very distorted, actually. It's lightly distorted. That's one of the challenges of the DES. So the source galaxies serve this kind of distortion that we call the cosmic shear. And when it feels this kind of distortion because of mostly the halos of dark matter. We can also we cannot look the halo of the dark matter, but we know that when you have an environment with high density, we have more probability to form galaxies. And we can, using these tracers, that are the lenses galaxies, in order to understand how the galaxies are clustered and how are the subjacent halos are clustered in the space-time. Finally, since we have this here forming around the halos and we have the source galaxies passing close to the halos, we have some correlation between both populations that we call the galaxy shear correlation. So we have several ways of getting some thing that we can compare with models, but the workhorse in cosmology is the correlation functions and the power spectrum. In this case, I'm calling angular power spectrum because we are just taking tomographic beams. We don't have enough information to do a 3D power spectrum. So we can see how preferentially covariantly oriented are the galaxies, and this is a measure of the cosmic shear. The correlation between the position and shape is exactly what we call the galaxy lensing correlation. So where you have more galaxy cluster, you are probably having more a larger or a more dense dark matter halo, and you are also having more shear in the source galaxies. Finally, the galaxy clustering is a measurement of how is the excess of probability of the galaxy getting close to each other, and this is caused by the gravity.
Sorry, can you just, just to understand correlation, the previous.
Okay.
So you're saying that those two things that are connected by an arrow are related to each other in some way? Is that what you're measuring, or what?
Yes, they are related to each other.
Is one supposed to be the same as the other? It's just that the lens makes it divided in two, or are they unrelated objects, or what?
Yeah, well, So this is a very good question because they are correlated and they have a very large covariance between stuff. But yes, this here we have some shear, and the cosmic shear. If you think just ideal case that your galaxies are randomly oriented, they are source galaxies, very far in the space time. If you don't have any shear, you're gonna have random orientations, and when we take the average, we're gonna have zero ellipticity. But the light that's passing through the halos is distorting this. This is not the end of the story because we know also that the source galaxies are not randomly oriented. They are also suffering effects of gravity that we treat in another way that I can detail later. But that's the idea.
So you say that the galaxies are uncorrelated, let's suppose, but the lensing somehow makes them correlated? Is that what you're saying?
Exactly.
Okay.
Ideally, galaxy would be correlated. This is not true again.
I understand.
But it's like you have, let me say you are very distant from the Earth, and you have something like this. And when you measure this correlation, the mean ellipticity is going to be 0. Of course, depending on how much galaxies you have.
Yes.
But when this initial setup passes through the dark matter halo or through the density field, it will have something that's going to make things. This is very exaggerated, okay, but that makes things with some very specific modes. And this comes just from the light passing, from the potential passing through these density fields.
Is there an intuitive way to understand it? For me, it would seem to be the opposite, that the lensing would tend to uncorrelate things which were correlated. But somehow you say after it goes to a lens, it becomes more correlated.
Yeah.
Is there an intuitive way to understand why that happens?
I'm trying to figure out why you think that when you pass the lens.
Suppose it was lens. Suppose it wasn't lensing. Suppose it was just some random thing which scattered stuff.
Yes.
Then obviously if something was correlated after, it's going to be uncorrelated because it went through some random garbage.
No, but this is if we take a single halo. This is the let's think about a point length, right? You're gonna have the gravity acting like this.
Yes.
And this is going to make everything that is this side here being more aligned for this specific mode.
Okay, I think okay,
yeah.
Thanks.
But this is a good topic to talk in my lecture. So thanks for the question. This is good. So I'm sorry. So again, the main probe for the dark energy survey is what we call 3x2 or 3x2 point correlation. So we take these 2-point correlations and we analyze them together. So we mix the different degeneracy to the parameters. And we also doing a joint analysis with more data, with more correlation. And this makes more robust constraints for astrophysics. And this is very interesting as well because the DS is able to do the measurement from all these populations. So we know that everything is controlled by the same systematics. We don't have to deal with hard tasks of reweighting different samples from different telescopes and different strategies. So, yeah. Again, I thought we would have more students, but even though I love this figure, it's explained very well what's happening. in the Dark Energy Survey. This is a cartoon made by Jesse Muir, our friend, and he's now in Permuter Institute. So this is the idea. When you point your telescope, you got a lot of images, and you need to classify them. So we have some algorithms for classification. And from this algorithm, we can throw away the stars. I'm against throwing away stars because they are useful for a lot of people. But for cosmology, we are more interested in the galaxy sample. So in the case of the shear, of the cosmic shear, we want to measure exactly this shape of the galaxies. So we have some codes like the meta-calibration that try to deconvolve all the effects that spurious effects that we don't want to consider, like a point spread function from the light passing through a atmosphere. And it takes you some very reasonable measurement of this shape and of its orientation. This is also important to stress. This is made in a very industrial way. So we can have big samples with 300 million galaxies, for instance. Other important information that we need for our cosmology is the photo-Z, is this information about the redshift. We don't have the full spectrum of the galaxies, but we can match them using some neural network like NZ and other methods, and try to assign reasonable values of the redshift for each galaxy. The redshift for each galaxy is not so useful for us, but it makes more useful when we combine them in tomographic beams. Finally, with this information, we have finally our cosmology machine, our cosmology constraining machine. So our cosmology constraining machine is calibrated by simulations. It also needs a very well validated covariance matrix. And also we need this component of the models. And when you do this, and we use some MCMC here, we have this very popular between cosmologists ellipsoid plots where we can see 1 and 2 sigma of the interesting parameters. And here is depicted the parameters that DS is more sensitive. That's how much the universe is clustered, and what's the content of matter, the density in the universe. I showed that before because this is a more realistic picture, but this is make everything more confused. But all the same ideas are here. So the multiprobe cosmology is some program that we are taking, and the TCP is very interested. That's combining different probes, not only the 3x2, but of course the 3x2 is very, very important, but also combined with the baryon acoustic oscillations, with this very specific preferential scale of the universe, causing after the decoupling, the drag redshift between the photons and baryons. Also, we want to combine our results with external CMB data. The DS also has its supernova sample, and we want to combine it then with the supernova because this way we can get better constraints. For instance, in the H0, that DS is not very good in constraining. It's not very sensitive. And finally, the gravitational waves in the form of bright sirens and mostly more now it's dark sirens, but I can talk about this in the future slides, okay? So just to give you some idea about what happened in the year 3, in the last public version of the DS, the DS cover almost 10% of the full sky with 300 million galaxies. We are very conservative on what we use for our sample because we need to having results that the community can rely. So the final cut, it has only 100 million galaxy shapes and 5 bands. And it has this shape noise that's, if you had infinite galaxies, you're gonna have 0 shape noise because you're gonna have no errors. And this, okay. Why?
You don't have nearby galaxies, 0.1, 0.01. Why you start at 0.2?
Yeah, that's a good question. I think we don't have a very sensitiveness for these galaxies. It's not in the sample. I cannot reply you properly, but yes, we just take from 0.2 and beyond. But we have these large errors from the photozip. Also, for instance, for the BO, we don't use even galaxies below 0.6 because we know that they don't give in a lot of signal for the cosmic structure. So after we have all this catalog, we can measure them. This is the measure of the correlation, the Xc plus, the Xc minus. This is the correlation between shapes of galaxies. The difference comes from the B modes, comes from the fact that this is not a perfect picture. And we have some contaminations, we have some intrinsic alignments caused by the original galaxies. But we have this both probes here. This here is coming from the galaxy-galaxy lensing. This is also very tricky to obtain because galaxy-galaxy lensing has some non-local features, and we need to exclude some of the data where we think it will be affected by a level of modeling that we don't have access for very small scales. And finally, the galaxy clustering. That's this correlation between the position and the galaxies, and of course, in its angular version.
Sorry, I got confused. Cosmic shear is supposed to be caused by these dark matter places, right?
Yes, by the
We
potential.
don't know the dark matter. How do you get this solid line? How do you get a theory
Oh,
prediction?
okay. This solid line here.
Yeah,
No,
what's the prediction based on? I don't understand.
What's the prediction? The solid line. Okay, the solid line is the best fit.
So there's no prediction.
Yes, this is the best fit
So
of
how do
this
you
data.
tell if your data is good or not?
That's an excellent question. I don't know if I should talk about this right now, but this is in the end of the process of analyzing. But we have several tests regarding the covariance, the goodness of fitting of the data. Sorry.
But is there some prediction you can make, for example, from one of these, get the other one, or something like that? I mean,
Yes. They are correlated. You mean they should be consistent to each other?
Dark matter distribution, right?
They have the same dark matter distribution, but the population is different because this is weighted by the galaxy that you are observing. Okay. But yes, you are right in the sense that they should have the same cosmological parameters. I guess Scott has a question.
Yeah, a couple of follow-ups. So when you say it's the best fit, what do you mean by that? Those lines?
This line, I guess this line is the best fit of of these measurements.
What do you mean by the best fit? The best fit in what space?
This is configuration space. This is the question, or not?
So you're saying, but it's generated by theory, right?
Mm-hmm. Yes.
So when you say best fit, what parameters are you varying to get the best fit?
I can tell you now, but this would be a spoiler for the next slides. But yes, here we have for the DS. I can move on.
But, I mean, let's come back to what Nathan's question. I think he was asking whether you can make a prediction for theory for these things.
No, yes, this is after the analysis and when we have the best fit. This is like in our papers.
But sorry, but forget about this stuff. The question, I think Nathan's question was was a straightforward one. Can you make a prediction for that data?
Prediction in which
Can you make a
sense?
prediction for what the theory should, what lambda CDM predicts, for example?
Yes, yes, but you need to also analyzing the best fit using all these cosmological parameters, because
So in other words, you can make a prediction from the theory, in other words. So that line is a prediction from the theory.
Yeah, I think maybe I'm not understand well your question. This is a prediction. This is a model. This is a model, but you will still need the free cosmological parameters. So you need to find the best fit.
So when you say best fit, you mean it's the best fit. You vary all the parameters, including the cosmological parameters, and you get this curve. That's what this curve
Exactly,
is.
exactly.
Okay.
And also the nuisance. Yes, exactly, exactly. Thank you, Scott. Thank you, Nate.
Parameters?
Yeah, I gonna skip this slide. So, yes, we
Sorry,
have.
actually, can I ask one more question? Sorry.
Yes,
You,
please.
um, you also said that the lensing is done by the dark matter. Is it only dark matter that does the lensing, or is it other matter? Or
No, 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 no. Sorry, it's all the matter. But
okay.
the lens here is very interesting because it's also sensitive, very sensitive to the dark matter. And since we know that this it's like 80% of the total matter, I just said lensing. But yes, this is imprecise. It's all the matter.
Okay, thank you.
Yeah.
Distribution of the dark matter, is that correct?
The parameters include the cosmological parameters, and we can predict the power spectrum from these cosmological parameters. So I can talk a little bit now about these parameters, since we are move on. So we have this all cosmological parameters. This is omega matter. This is the amplitude of the power spectrum. This is the index, NS, omega baryon, the rate of expansion, the density of neutrinos, and the W here is for the equation of state of the dark energy. So yes, in this sense, you can use a code like CAMB, Boltzmann solver, and you get your power spectrum. But this pure power spectrum that you obtain from CAMB or from older versions of CAMB, it's not enough because we need to account for our population of our sample of galaxies. Well, we are not actually observing the P of K, but we are weighting this for how many galaxies we are observing. So that's why we have several other parameters. And this here is associated to the error that we made in our photo Z assumptions and in our photo Z estimates, actually. This comes from the intrinsic alignment that the galaxies are not, the source galaxies are not loose in the space. They are also suffering and affecting each other. So we also have the source photo Z. It's the same of the other one. It's related to the error that you have in your determination of the redshift. And we have some the calibration from shear from the magnitude. Of course, we have the lens galaxy bias that's telling you, this case is the linear, that's telling you how likely is to find a galaxy and when you have some subjacent invisible matter in the halo. Okay. So I'm sorry, I'm going back a little bit because something that's very, very important for us is the covariance matrix, at least for me, because I work a lot with this. But that's it. With great statistical power that only the DES and the other big surveys have, it comes a great responsibility. So in order to know that we are doing a good job and that we are fitting properly and that we are understand the universe, we need to using this code for covariance. And we can see that we have a very, very correlation between different probes. between, for instance, the correlation function and the correlation function in different beams, for instance. So in order to make sure that we are doing everything right, we have this all reported in this paper led by Oliver. I work with Hugo, and Rogério was also working in this paper, worked a lot, where we test everything that we could test about covariance matrix. So we test if the likelihood, Gaussian likelihood was good enough that we know the Gaussian likelihood is some kind of approximation for our kind of probes. We test the effect of tri-spectrum. We test the theoretical covariance. So we test what's the effect of guessing the wrong number for the cosmological parameters that create this prediction. We test how the footprint of the survey, how the fact that we are not observing the whole sky, but just a region, and this region with a lot of fractal structure is affecting our results. How the non-Poissonian shot noise is affecting our errors. The fact that we use angular beams that we are not using, that we had to bin in our data. All the galaxy weighting schemes, redshift space distortion, curved sky, etc. And for this, you create some linearized likelihood where we had some simulations. We knew what was the best fit, so we could do very small variations. We did the chi-square approach, and we also test if the parameters estimated were correct. This, we create 60 terabytes of simulation for 3x2 and for the 5x2. So thank you very much, EFT, because we use GridUNESP a lot. And we also created one more terabyte of simulations for B modes and for galaxy-galaxy lensing systematics. Although this number looks big, most of the computational power comes from estimating and the measuring the correlation for each of the simulation, because it's, naively speaking, it's counting pairs. And the counting pairs and comparing also with random pairs. So yes, we use a lot of hours. So finally, a little bit more about theory and data. So this is some pictorial idea in the paper produced by Sarah Bridle. And this is very useful to understand how hard it is to measure the shapes. So this is an intrinsic galaxy. This is a galaxy free in her environment without suffering without the light suffering any kind of distortion. But the gravitational lensing makes things stretch, not with this amplitude. It's exaggerated. And when this stretch passes through the atmosphere causes the convolution, and it blurs everything. Also, we use CCDs, and CCDs are actually the best choice for doing this, but CCDs have pixels, and we have a limiting resolution. Also, we also have some noise that comes from the image. So besides the vanilla theory of just think about what we see in the textbooks, we also need to deal with a lot of extra layers of theory with nonlinear bias, intrinsic alignment models, the calibration of the photometric redshift, the multiplicative shear calibration, and also we need to deal with the effects that we are playing with the nature. So we need to deal with point spread function, response function, photo calibration again, and the blending. Blending, I didn't mention this, but this is more or less like an image that we observe. But if you don't have a very good resolution, or if you have a very small object, I hope Scott can see the blackboard. Something that you can see like a big blur in that orientation. It might be actually several galaxies in other orientations, and you may be dealing with wrong information. So, so this process, this whole process, maybe the final lesson is about this whole process, is that we need to be humble on how much we can observe, how much data we can collect without compromise our results. Okay, I talk about this. So now this is the basic set of parameters. We deal in this setting of parameters with the basic ingredients are the likelihood, and we now also need some data covariance and some data of likelihood. We need some halo model for the covariance for dealing with the non-Gaussian part. We did the models with parameters P, and these parameters P are all here. Only the 7 here are related to the cosmology, but we need to properly address all of them, all of these nuisance parameters, in order to be sure that we are giving the best answer and also the most accurate answer. We need some criteria with measurement to combine. We need some idea on which kind of probes we can combine. For instance, if you have something that's very intention, it doesn't make sense you combine another experiment with your experiment with another experiment with intention, because you may be combine things that are not compatible, maybe by systematics, maybe by physics. And finally, although the DS people are amazing and the cosmologist people are very, very competent, we are all human. So we have some blinding schemes to minimizing the observer bias. We have some blinding in order to ensure that when you try to formulate your pipeline, you are not trying to reproduce something that already was existing in the literature. So this is very classical for the instance, the Millikan problem of measuring the charge of the electron that people, he was very very famous and a brilliant scientist, but he made a mistake, and you can see along the time people converging slowly for the correct value. So in this case, when we have the blind scheme, we try to avoid this in order to say if we have something new, we know that we are not just trying to make something different from an existing problem. And when you have something that's consistent to the other experiments, we try as much as we can make sure that we are just not replication all the results. Okay. So a little bit of the results, a little bit of what we measured and the DS. Again, this is for the year 3 analysis. We are going to have this summer in the North Hemisphere new results. So the DS, the 3 times 2, it gives this value of the clumpiness. SE8 and the sigma 8 is a measure of how clumpy is your universe, because this is the variance of the matter fields. And this is the matter density. We see that we have some difference from the Planck, from the results from Planck. But given the size of our posterior, the error bars, basically, you can see that this is, we can consider that this is not in a big tension. This is different, but this is, given the error bars, it's not properly a tension. So this here is trying to understand if we have some tensions when you observe probes in the low Z, in the local universe, and probes in more distant universe. Again, the 3 times 2, this here, is very sensitive to the S8, but for the omega M, it's not so sensitive, but it's still very, very interesting results. And we can see that we don't have tensions between both cases. So this is testing the equation of state of dark energy. So assuming a constant equation of state, and if this is equal to -1, and the dark energy has a constant equation of state, we have the lambda, the cosmological constant. But it's very worth to see if we can observe some deviations. And here it's very consistent. The combined data is very consistent to this to the lambda CDM. In some of the next slides, I'm gonna show updates on this result. So finally, we have the combination between DS, supernova, BAO, and also 3 times 2 supernova and Planck. We can see that is the Planck result. We can see that the DS is having a lower clumpness of the universe. We have lower variance of the matter. But again, given the size of the error bars, we cannot say that this is this is not intention, strictly speaking. Okay. So talking a little bit about the dark energy harmonic space. I want to talk because we have some very nice people coordinate. Hugo, my dear friend that shared the Office 205 with me for years, and my student Lucas. And this is an effort that started with Rogério. Rogério proposed this kind of analysis. And in the harmonic space, we try to, instead of using the correlation, we're using the angular power spectrum of galaxy positions and shapes. This is an independent analysis to the configuration space, so it's also useful to see if we have robust results. For instance, for using simulations for covariance, this is way faster for doing the measurements. For instance, Lucas, Hugo, and I developed a code for doing on-fly simulations and measurement. And we can do a lot of them for covariance in less than 1 day. And for the configuration space, I spend more than 1 million hours, CPU hours, to measure the correlations. So also in the covariance space, we have less mode mixing. So it's easier to understand which scale belongs to which scale. And this makes it easier to understand until which scale we are considering your data. Because we know that we can model a very large scale, we can model moderate smaller scale, but we cannot model in our cosmological model, for instance, the chairs of this auditorium. So we always have this limitation. Of course, way above the size of the chairs. So giving a brief overview, we have several papers in harmonic space. This paper of clustering was led by me, but always with a collaboration of Hugo and Rogério and Lucas. We analyzed the shear in the year 1. And Cyril Du, our colleague in France, did this very nice paper comparing how is the shear in configuration space related to the harmonic space. And we finally got to this combined analysis that is led by my student, Lucas. And here we are going to the year 6. For the BAO, it says a different story. The BAO started with Hugo, Nick, and I, and Rogério, of course. And the BAO in the year 1, we did the independent constraints, but for the year 3, our results was combined with the configuration space. And this way, we could improve a little bit more our measurement of this BAO scale. And this was the standard analysis now for the year 6 that I will talk later. So just showing this nice result from my student. We showed, this is internal review in the DS, so this is not public. but I'm showing this comparison between configuration space and harmonic space. For harmonic space, we did two different configurations. Here we went to smaller scales, so we have more information, and here we went to just to larger scales. And for configuration space, they went to smaller scales, but these smaller scales were down-weighted by the covariance and for something called point mass marginalization.
Sorry, I'm lost. So you're taking data from some experiment and you're somehow manipulating the data to get these graphs? Is that what you did?
We are taking the same data from the DS, but instead of using the correlation function, instead of using this, instead of counting pairs, we calculate the power spectrum. It has some difference between the configuration space and harmonic space because the scales here is not very well translated because it has a lot of mode mixing. If we had infinite modes available, if we have a full sky observation without our galaxy, for instance, it would be perfect equivalent, but this is not the case. Also, when you are looking for the harmonic space, instead of measuring the ellipticity, we are measuring the E mode, and we are not suffering from some thing that we call non-local problems.
Okay. I'm just trying to understand why you're doing this. What you're trying to compare with something else, or I'm kind of lost.
Yeah, we have the same sample of galaxies, but we construct maps. The sample of the galaxy is not the end because you need to also modeling. And as I said, we have the sample of galaxies, and you need some summary statistics to transform these in something that you can compare with your model. So the standard way is getting the correlation function. And we are showing that we have a slightly different modeling. We are not using all the data that the configuration space is using. This is some other summary statistic that's combined here. And in the end of the day, we have something that's reasonable, which is great, it's expected. But we have this different analysis. This is also proof of concept because for the LSST and for the Euclid, we are discussing using the harmonic space analysis instead of the correlation space, the configuration space analysis.
Okay.
Okay.
So it's a new way of analyzing the data. Is that what you're telling me?
Yes.
That's what harmonic space analysis means?
It's a new way.
Okay.
It's not simple as it looks because you need to deal with the math.
It's complicated. I'm just trying to understand why it's useful. That's what I'm trying to understand.
Yeah, no, that's a very good question. Okay. That's a very good question. Okay. But this is useful because of this. We are also treating the survey features in another way, like the mask and the footprint of the survey. And this is also useful for when we have way more data and we need to analyze we need to get more computational power. We show that this works, this is consistent. And for the year 6, we are also having some difference in the modeling. Okay. But this is a very interesting question, indeed. So talking a little bit of the BAO measurement, the BAO appears in the configuration space as this bump in the correlation function. This is reduced from a smooth version of the correlation function. Or in the harmonic space, it appears as wiggles. So the first harmonic space detection in the DES was made by us. Rogério was our boss. And we could detect this BAO signal. And for the first case, we are showing that this is consistent again. So we show that we have some consistent results with the feature that you observe in the configuration space. But as I mentioned before, the scales are not very translatable. So when you look the covariance between of the harmonic space and the configuration space, it's not exactly 1-to-1. So when you combine both, you have a little bit more signal. And the BEO and in the photos survey, where you don't have a lot of information, the redshift is a hard thing to measure, because exactly you don't have this precision in this radial direction. But here I'm skipping for the year 6, but it's very interesting to say that before DESI, and I will talk about DESI soon, but before DESI, combining both detections, we had the best measurement of the BAO scale in this high redshift in the history. This was the best data. Of course, now DESI is coming, and I will talk about how DESI has changed all the game. But yes, we have a 2.1% detection, thanks to combining, thanks to all the hard work of creating samples and to combine the different.
It's a bit hard to follow. I think it's probably trivial for half the audience and too complicated for the other one. I think it's a bit hard for people that are, I mean, for Rogério and others, it's obviously trivial, but for us, it's too qualitative. It's too qualitative, and then there are a bunch of plots. Can you explain a little bit what are the, I don't know, what are the key physical ideas? You just have, because otherwise it looks a bit like what Nathan is saying. There is a lot of data, okay, and someone analyzed it. But what should I be taking out of this talk, more than that?
Yeah, okay. So the BEO, it's measuring this specific scale that's formed when the photons and the baryons decoupling in the space in the past. This happened after the decoupling from the CMB. So we have the sound wavings that form the anisotropy from CMB and caused by the matter fluctuation. And the BEO, these sound waves, when the baryons finally code the coupling of the photons, and we have way more photons than baryons, so it takes a little bit more. But this scale of the sound waves keeps some imprint in the galaxy distribution. So basically, when we look for the power spectrum, we're gonna have. Sorry.
No, I'm trying to think of how to formulate a question that helps me get something more about all this data analysis. So you have these terabytes of data analysis, right? And then there is boring work and interesting work, right? So there is some work that you tell your student, okay, please do this, someone needs to do this, try to parallelize this or something.
Yeah.
And then there's interesting work where you think, oh, I need some new idea, I'll go to Fourier space, I'll try to decouple the various modes and so on. Can you help us, what are the interesting ideas? Separating, can you help me separate a little bit what is just hard work that you need to do from some interesting, from the ideas that I should be taking? Because even if it's mostly about data analysis, I'm sure there are interesting things inside.
Yes.
I'm just
indeed.
not being able to get what they are. What should be the tricks that I should be learning to try to use them elsewhere, or that I should be aware that they exist?
This is an excellent question. Yes. So basically, when you find this bump, I will talk a little bit about the data for a while. But when you find this bump in the matter distribution, this excess of probability, this is caused by the baryons and by the sound waves traveling, and after the decoupling, they will form a little bit more galaxy in that region. So this is a very fixed angular scale in the universe. So this is a standard rod. You know, if you know where is this bump here for a given redshift, you can use this to constrain the expansion of the universe. Because we know you're gonna know that something with this size here is arriving to the observer here, and that this is at a given redshift. And if you have, for instance, some curvature, you see that the observer is going to observe some angle like this or some other angle like this, some curvature in the universe. So this is an excellent question. Thank you so much. But this is a measure of the standard rod of the universe that you can use to map how fast is the universe expanding, and you can use this to understand also the structure or the curvature of the background of the universe. Yes, but it's a lot of data analysis and hard work, but yes, the physics is here. So if you find something, so here is what's the data. So this is the comparison to the reference, that's the Planck cosmology. So let me say that we don't have this error bar with this size. This would show you that you have some tension. We have some unexpected physics happening in the background. So it's very compelling. And that's not very compatible to the standard model. So yes, this is help you to map the universe across different redshifts. But yes, I was focusing on how hard is to get to this, but yes, this is the idea. So now with DESI, we're gonna have, we are already having smaller measuring of these bars, and we can use this also in the radial direction to, instead of measure the H naught, the local expansion, now in DESI we are able to make measure on how the universe is expanding at a given redshift. This is super, super cool. Oh, sorry. Uh-huh.
Done also when you were here. Is that what you're working on now, or are you working on different things now, or?
No, this started, but the last results came this year.
But it's the same kinds of things.
This is the same kind of things for this, yes. But I'm doing other
What
kind
are the
of
other things you're doing?
yeah, I can move on so in my presentation.
Because it's already.
Oh, I'm so sorry. Yes, yes. Okay. I won't talk very quickly about the supernova. We have this sample from supernova and the DS. Something that's very interesting, we are find some WA that W naught slightly favored by the data instead of the lambda CDM. So our sample has five more high quality supernova in high redshift than the other leader. And with this, we got some difference in the WA and W naught. We are having some, for a while, not very strong evidence of something that's dynamical. Something that I've been also doing with Marcelli is trying to also measure the DL and measure the H naught from the GW. So this comes from an idea by Bernard Schultz, and he shows that when you have the coalescence from a compact binary, this would be inversely proportional to the luminosity distance. And with this, you can get your luminosity distance without suffering with all the calibration of the cosmic distance ladder that other probes have. But on the other hand, we don't have a redshift for this, and we have some other kind of correlations. So for now, we just could find the redshift of a single event. This is Marcelli was one of the leaders of this finding. But the idea is to combine with using also dark sirens and getting some constraint, combining the catalogs and the GW signal. Yes. For this, I also work with this NOMAS, where we formulate some forecasts for when we find more counterpart in electromagnetic. And this is just a comment. So finally, I'm getting to the dark energy spectroscopic survey. This is the next generation. This is what's happening right now. The BO is happening in February, but now in April, all the best BO data is coming now from the DESI. So we are made by 900 members. The operation is going to last for 5 years. And in these 5 years, we want to observe 30 million galaxies. And we are doing this in a very, very quick pace. We can get up to 100,000 spectra every night. So here is something, because I was here in this case, but this is the project that I led when I was a postdoc here. And this was great because we could get 2 PIs for the DESI with this work. And this saved us $400,000 in the time of Bolsonaro. And we try to keep the science working here, and I'm really proud of this. But this is related to the observations. And very quickly speaking, what the DESI does is amazing, because in the past, in order to observe the fields, you need to have an aluminum plate, and you need to make holes in that and plug. And now in DESI, we have 5,000 positioners. I don't know how to run this. This here, okay. We have these 5,000 robots working all the time in a constant pace and getting more than all the other experiments ever have done, and that's in a single year. So the movement of these robots, they have a precision of 6 microns. This is a scale smaller than a blood cell. And with this, we can point very tiny, very thin fibers and collect a lot of data from your desired field. And we collect a high-quality spectrum. This is what we did in Michigan. So although the project is a success, after a few months, we lost almost 15 or almost 20% of the robots by some mysterious problems, because the robots are really tiny. This 3 gears is in this space here, so you cannot see this properly, and you cannot stop the operations to do this. So what we did is creating a replication of the telescope operations. I did this with my dear students and the lab friends. And this is the first time that we saw moving the positions in very strange positions, orientations, and doing long stress tests. We could see how they break. When it's one, it's the requested movement, is the reproduced movement. So we saw they breaking, we saw they getting crazy, and we saw they recovering. And this is our contribution for the focal plane team for the DESI. So talking about DESI, DESI goals is measuring the expansion of the structure of the universe. With this, we want to use this for formulate better models. I do care about this because when I PhD working with phenomenological models, we had a lot of amplitude to propose new things because we don't have very precise measurements. So the idea of this is that we can use the standard rules that I mentioned here before, and we can measure also the expansion in different redshift. We can measure the redshift space distortion because when you're observing this spectrographic survey, you're gonna see the distortion that comes from the redshift. We're gonna see this kind of effect here, and this is related to the potential of that your galaxies are inside. Also, with DESI, we can do a better measurement of the equation of state of the dark energy. And using the growth of structure measurements, we can also try to distinguish between very similar models of dark energy. Models that in the background has the same behavior. We see the same rate of expansion, but when you observe the structure formation, they are very, very different. So again, for this here, DESI is using the template fitting. This is Jiamin Pen. He was my mentee at University of Michigan. We did this work where we show that for some specific modified gravity called a home desk model and modifying also the background, we could use this kind of approach safely, both for the DESI and also for the future experiments with a very, very high precision like the MegaMapper. So this is what DESI has done. This was published.
How many more slides do you still have?
Yes, I have a few of them. I can short this and just show the results.
It was supposed to be 1 hour, right? Or
Yeah.
no?
Okay. If you want, I can stop now. I just want to show that very quick results. Okay. So here is the consistent between different probes. We are observing things up to the redshift 4. We show that we have the constant equation of state if this is the case of the universe. This is consistent to the lambda CDM. But when you combine with the supernova from DES, we can see that we have some indications for the dynamical dark energy. We have a 2 sigma away from this. This can serve as a motivation for finding other models beyond the lambda. This is only the first year, so much more has to come. Also, something that we did is measure the neutrino masses. We have some 2 sigma favored for the normal hierarchy. But again, this is the first year of result. We gonna improve much more with the last years of the experiment. So the future is, I'm showing the LSST that I'm a member. I'm one of the 25 pipeline scientists of this group of 1,200 members. The LSST is going to start to operate next year, hopefully. The camera is already there, and it's going to collect 20 billion galaxies. And this is going to collect shapes, and this is going to collect to measure correlation like never, and make real-time moves of the universe. Just showing this here, we are producing our theoretical and our modeling, and it's public, so everyone's welcome to collaborate. Here is the desk domain, and here is the TJP-COV that I'm one of the leaders. The TJP-COV, this is the team with Rogerio again here, Carlos Garcia, the former coordinator with me from Oxford, Davi Alonso, Lucas, Masahiro Takada, that's a leader in this field. And also, when I was, I had 2 co-advised students here that worked with the covariance. Gabriela and Abdias were both advised by Rogerio. So we have some methods of mitigating the error when you don't know properly what's the right barrier model. And we have this work that is in preparation. It's a dissertation, but it's going to be a paper with Nikki, Abdias, Rogerio, and I that dealing with mitigating the error when you don't have a full model of the halo, the galaxy, and the halo connections. We are now starting a new collaboration with the EPFL and the Berkeley National Laboratory, where we are going to test the positioners for the Mega Mapper. We are calling the Astrobots, and we have Mega Mapper is going to be a very, very interesting experiment because it's not only bigger than DESI, but it's going to be placed in the very side of the LSST, so they gonna observe the same field, and we're gonna do science together finally. Because one of the things of the DESI is that it was built in the North Hemisphere. So we cannot properly combine data from both experiments. So final remarks, I'm super sorry for taking this long. The name of the game is the combination of the data. It's a lot of work, but this is something that I think it's going to be relevant both for the observational cosmology and also for the theorists, because we want to understand if the universe is really accelerated by the lambda or by something different. In any case, both answers are very interesting for the community. It's interesting that after 26 years, we don't know exactly what's the dark energy, but we know that it's contributing more or less with the same energy density. And we are starting maybe to have evidence of exotic dark energy models, or maybe the exotic gravity. We have no significant tension between the early and late universe, but we still need to understand something that should be very basic, but it's really hard to address, is why supernova is observing the universe expanding in a very different rate than the CMB is observing. Okay, many opportunities. Again, I thought we would have more students, but we are doing a very interesting new experiments. We're gonna have our results from the DS year 6, and then we are going to update the DESI, and we're gonna point DESI more to the south to have more correlation. LSST is starting. LSST thing that's going to be very important is the synergy with the space experiments like Euclid and Roman. We hope that we can find more electromagnetic counterparts for the GW Cosmo, and a lot of things doing in all this experiment related to modified gravity, alternative dark energy and dark matter model being tested, and we have some fields that's going to be very relevant for the next generation of surveys, like the harmonic space analysis and also simulation-based inference. So thank you very much.
I don't know what Marcel does, but are you doing anything experimental or no?
Experimental?
I don't know what she does. What exactly does she do, Marcel?
Oh, yes, instrumentation, right?
Sorry?
Yeah. Instrumentation, I'm doing
Yeah, yeah.
instrumentation, yes. Yes, I'm working with instrumentation. This is a way of also having grants. And so the 25% of my research with Marcel was working with instrumentation, and joined the projects.
But is this something you're going to do in the future, or is it depend on your grant? Or I'm just trying to understand what your plans are.
I think I like this question. I think I got traumatized by the period after with Bolsonaro, and thanks to the in-kind contribution that we could keep working in the big experiments. So I want to, any place that I go, I can still have access to state-of-art experiments. So that's why I think it's useful to have a small component of this.
I don't think you answered my question. Are you planning to do instrumentation in the future or not? It depends on the government? I don't understand.
No. It's I want to do something government-proof. I do plan it to have some component, a small component, but I do plan to have something to.
But most is theory. Is that what you? When I say theory, I mean not instrumentation. Is that correct? Or?
Yeah. Yeah, but for instance, when I work with the KLF, this is not instrumentation, but this was support. I was a postdoc here, and we had a collaboration with Linea. We have people in USP, so I think it sounds like a strategy, a good strategy to me. I don't know what you think.
But the pipeline you're part of, it does not involve instrumentation, or it does involve instrumentation, or?
The pipeline scientists, no. Yes.
Okay.
Yes.
So your role in these experiments is theoretical. It's not instrumentation.
Yes,
okay.
but yeah, I was doing. I'm starting to work with mega mapper instrumentation. So when we have the instrument ready to go, we want to have access. We want to have the state of art. So yes.
I have a question on the. So you showed the sigma 8 omega m, and you said there is no tension with Planck, but other experiments they say there is a tension.
Sorry, a detention with Planck?
Yeah, on the sigma 8 omega matter parameter, DES claims no tension with Planck, but I think kids say there is a sigma 8 omega matter tension.
Yes. Kids is other case, but yes, for the DS we didn't observe this tension. This is actually a very, very weak tension, so we don't want to overweight the word tension because people may understand that, okay, we are saying that the physics is broken, so we need to have some degree of certainty to say, okay, this is a tension that's maybe systematic of the physics, but that's the message here.
And has there been like joint working groups between KITS and DES to try to see if this is a statistical fluctuation or this is a pipeline that makes different analyses or different assumptions? I don't know.
Yeah, we actually have a paper that I worked with KITS cross DES. We show that it has only a small level of tension, but it's not something, maybe in the future with better precision, we can see something more drastic. And also, it's tricky to combine both experiments because you need to understand they have some overlap. And in our case, we remove this overlap from our footprint and try to do the combined, the consistent analysis. So you also had missed a little bit of information.
Thank you.
Can you say a few words about your projects with the dark science?
Yes, we have different things happening. So let me see. So we have this project that was for the snow mass. Here, the idea was to say if you have a different model of the dark energy and the underlying, in the true model of the universe, and you try to fit with the lambda CDM, this will going to create some shifts. And when you combine different experiments, we could see some tensions and we could see some indications of new physics. The other projects are related more to the searching of counterparts. So we are taking, I don't know if you're familiar to the BILB, but we take the astrophysics parameters from this code called BILB, from the GW string. And we mix with the galaxy catalog and say that instead of having the full map of the GW, we gonna have just these possible positions given by the galaxy that could be the host. And with this, we reduce the list of the candidates, and we can reclassify and try to find counterparts in a better way. Other thing that I've been doing with Marcelo, we create a pipeline for the GW cosmology that integrates to our standard DS pipeline that's called Cosmosis. And with this, I taking the posterior, the astrophysics of the GW and the constrained chains, make a KDE, and with this, we can use as input for combine with the 3x2 data in the DES. This is showing a very, very small improvement. It's not. Both GW and DS are not very good. Hopefully, GW is going to be way better than the DS, but the DS is not an experiment that's very sensitive to H0.
Thank you.
Thank you.
Suppose you could build a camera which had infinite precision.
Oh, okay.
What would you do with it? I mean, what would you learn from it? Obviously, you'd take pictures, but what would you learn from those pictures?
If you had infinite precision, you're
Yeah.
gonna have a lot of information about redshift space distortion.
Yeah, but how would it help solve those three big questions you asked at the beginning?
If you have infinite precision and infinite time,
Yeah.
you're gonna properly measure all the potential in your galaxy. So you're gonna see the inflow of the galaxy in your radial direction.
Yes.
And this is for larger scale. This is just the Poisson equation. Yeah, you're gonna have something like yes, I guess. So you're gonna see the density fields itself. You know, you're gonna see the matter fluctuation, even the dark parts.
Okay, and how does that help me understand the three big questions you asked about?
This this would make a very precise inference about your cosmological parameter, about your fluctuation. This will show, for instance, if we assume that model, the lambda CDM, the constant cosmological, is the final model of the universe, and you can.
So let's do that. So how do you use this data to tell me if the cosmological constant is the right theory of dark energy?
You can use this to check the expansion, and you can use this to check how the structure is being formatted, and you can see that the early universe is having exactly the same model underlying as the closed universe.
Okay, so that's the main ingredient. So you would compare the universe at different times and see.
Exactly.
Okay.
This is more or less what we are trying to do with DESI, because we are observing the redshift space distortion in different redshifts, and also the expansion in the radial.
Okay. The other question I had is, so we heard a talk by Luis about CMB lensing. And I asked him a question, and I'll ask you the same question. Can you compare your lensing with his and see if they match or not?
Yes, but I talked a lot, and it's not everything, yes. But, okay, I didn't put anything here, but we actually do this actively in the TCP.
And they match? The lensing?
They match. Yes, they are in agreement. We don't see any strange.
I see. Okay.
Yes.
In different regions of space, you can say, "Oh, there's a lens, there's a lens, there's a lens." And you can
Yes,
compare
and you take the convergence field and compare with the matter field. Yes, yes. We are trying to do everything to break the universe, to break the models. But yes, and
Okay, so let's think.
Yes, half past 2. Thank you.